Welcome to this problem walkthrough. Today, we'll be solving problem number 1234, titled Replace the Substring for Balanced String. This is an interesting problem that tests your understanding of string manipulation and sliding window techniques. Let's dive in. In this problem, we are tasked with making a given string balanced. A string is considered balanced if each of the four characters Q, W, E, and R occurs exactly n divided by 4 times, where n is the total length of the string. The input to this problem is a string that only consists of these 4 characters, and our goal is to determine the length of the smallest substring that can be replaced to make the string balanced. Once we identify the substring, we can replace it with any other string of the same length to achieve balance. For example, in a string of length 4, each character should appear exactly once for the string to be balanced. The output for this problem is an integer that represents the length of the smallest substring that needs to be replaced. Let's look at an example to understand the problem better. Consider the input string QWER. Since each character Q, W, E, and R already appears exactly once, the string is balanced. This means we don't need to replace any substring to achieve balance, so the output is 0. Now, take the input string QQWE. Here, Q appears twice, while W and E appear once each, and R does not appear at all. The target count for each character is 1 because the length of the string is 4, and 4 divided by 4 equals 1. To make this string balanced, we need to replace one occurrence of Q with R. This means the length of the smallest substring to replace is 1. To see how this works, we can replace the substring Q at either index 0 or 1 with R. Doing so ensures that all 4 characters Q, W, E, and R each appear exactly once, making the string balanced. Thus, the minimum length of the substring to replace is 1. Now consider another example, the string QQQW. In this case, Q appears 3 times, W appears once, and both E and R are missing. The target count for each character remains 1 since the string length is 4. To balance the string, we could replace the substring QQ at indices 0 and 1 with ER. This ensures that each character appears exactly once, and the minimum length of the substring to replace is 2. Now let's discuss the constraints and edge cases to keep in mind. The length of the string, S, can range from 1 to 100,000 characters, and the string only contains the characters Q, W, E, and R. It is guaranteed that balancing the string is always possible by replacing a single substring. Let's consider a few edge cases. First, if the string is already balanced, like QWER, the output is 0 since no replacements are needed. Next, if there's only a single character in excess, such as in QQQE, the smallest substring containing the excess character must be replaced. Lastly, for a very large input, such as a string consisting of 100,000 Qs, an efficient approach like a sliding window is necessary to identify the minimal substring to replace within the constraints. To start, let's consider a brute force approach to the problem. The idea here is straightforward. We replace every possible substring of the input string and check if the resulting string becomes balanced. A balanced string is one where each of the characters Q, W, E, and R appears exactly n/4 times, where n is the length of the string. Using a sliding window technique, we can generate all possible substrings, replace the characters within that substring, and then verify if the modified string satisfies the balance condition. However, this method is computationally expensive. Generating all substrings alone requires n² time, and on top of that, checking for balance after each replacement adds even more overhead, leading to an overall complexity of n³. While this approach is conceptually simple and easy to understand, it is impractical for larger inputs due to its inefficiency and doesn't take advantage of opportunities to optimize based on the problem's constraints. Now, a more efficient solution involves optimizing the sliding window approach. Here, the key insight is that we don't need to replace every possible substring. Instead, we focus on identifying the minimum substring that needs to be replaced to achieve balance. The problem can be reframed as finding the smallest window within the string that contains all the excess characters, those that appear more than n/4 times. Once this window is replaced, the string becomes balanced. To do this, we start by calculating the frequency of each character in the string to determine which ones are in excess. Then, using a sliding window, we dynamically adjust the window size to find the smallest substring that reduces these excess counts to 0 when replaced. This approach leverages the sliding window mechanism to efficiently shrink and expand the window as needed, ensuring that we maintain the balance condition outside the window while minimizing its size. Since the window adjustments happen in linear time, this method achieves an overall complexity of O(n), making it significantly faster than the brute force method. The trade-off here is that while we gain efficiency, we need to carefully manage character frequencies as the window moves, which requires a bit more complexity in implementation. Ultimately, the optimized sliding window approach is the chosen strategy due to its balance of efficiency, scalability, and simplicity in implementation. With an O(n) time complexity, it is well suited to handle large input sizes, which is essential for competitive programming and real-world scenarios. Unlike the brute force method, this approach scales effectively as the input size increases, making it both practical and performant. Additionally, while the sliding window mechanism involves dynamically managing character frequencies, it is still easier to implement compared to more advanced data structures like segment trees. As for the brute force approach, although it provides a useful baseline to understand the problem, its O(n)³ complexity makes it infeasible for larger inputs. The trade-off with the sliding window approach is that it doesn't explicitly enumerate all substrings, focusing instead on efficiency. This sacrifice is reasonable given the problem constraints, as the method directly targets the smallest substring required for balance. Overall, dynamically adjusting the window to replace only what is necessary ensures an optimal and practical solution to the problem. To solve this problem, we start by understanding what it means for a string to be balanced. A balanced string is one where each of the four specific characters Q, W, E, and R appears exactly n/4 times, where n is the length of the string. If any character appears more than this threshold, it creates an imbalance. Our goal is to determine the minimum length of the substring that we can replace to fix this imbalance and make the string balanced. To approach this mathematically, we calculate the excess frequency for each character. This is the amount by which a character's count exceeds n/4. If a character's frequency is already less than or equal to n/4, it doesn't contribute to the imbalance. If all characters meet this condition, the string is already balanced, and the result is 0. Otherwise, we know we need to address these excess frequencies to restore balance. To efficiently find the minimum substring to replace, we use the sliding window technique. The idea is to maintain a window, defined by 2 pointers left and right, that dynamically adjusts as we process the string. Starting with both pointers at the beginning, we expand the window by moving right and updating the frequency of characters inside the window. At each step, we check if the characters outside the window satisfy the balancing condition, specifically, whether their frequencies are less than or equal to n/4. If the condition is met, we can attempt to shrink the window by moving the left pointer inward, ensuring that the window remains valid while we minimize its size. Throughout this process, we track the smallest valid window size, as this represents the minimum substring length needed to balance the string. This method is highly efficient because it avoids the need to check all possible substrings, which would be computationally expensive. Key insights about this algorithm include the efficiency of the sliding window approach, which reduces the time complexity to O(n) by processing each character at most twice, once when expanding the window and once when shrinking it. Additionally, the balancing condition focuses only on the characters that exceed the n/4 threshold, simplifying the problem significantly. Edge cases are also important to consider. For instance, if the string is already balanced, the result is 0. Another edge case arises when the string length n is not divisible by 4. In such scenarios, the balancing threshold should be calculated as the ceiling of n/4. The algorithm relies on two key data structures, a hash map to count character frequencies, which allows for constant time updates and lookups, and 2 pointers to manage the sliding window. Together, these ensure a highly efficient solution with minimal space usage. Finally, let's look at the implementation. We start by importing the counter class from the collections module to calculate character frequencies. After determining the target frequency for balance, n/4, we check if the string is already balanced. If it is, we return 0. Otherwise, we initialize the sliding window with 2 pointers, left and right, and iterate over the string with the right pointer. For each character at right, we decrement its frequency in the hash map. Next, we check if the characters outside the window satisfy the balancing condition. If they do, we attempt to shrink the window by incrementing left, while updating the frequencies accordingly. During this process, we track the minimum window size. Once the loop completes, the smallest valid window size is returned as the result, giving us the minimum length of the substring to replace in order to balance the string. This Python solution implements the sliding window technique to solve the replace the substring for balanced string problem efficiently. Here's a breakdown. 1. Initialization. The string length n is determined and the target count for each character, q, w, e, r, is calculated as n//4. A counter object is used to track the frequency of each character in the string. 2. Early exit. If the string is already balanced, i.e., all character counts are less than or equal to the target, the function immediately returns 0 as no replacement is needed. 3. Sliding window setup. The min_length variable is initialized to n, the maximum possible substring length. A left pointer is set to the beginning of the string to help define the sliding window. For expanding the window, the right pointer iterates through the string. For each character, its count is decrement in the counter to simulate removing it from the current substring. 5. Shrinking the window. After adjusting the right pointer, the algorithm checks if the remaining portion of the string, outside the window, is balanced. If it is, the min_length is updated with the current window size, right-left +1. The left pointer is then increment, and the corresponding character is added back to the counter to maintain correctness. 6. Result. The process continues until the right pointer has traversed the string. The smallest balanced substring length found during the traversal is returned. This approach efficiently finds the minimal substring to replace in n time, as each character is processed at most twice, once by the right pointer and once by the left pointer. The use of the counter and the sliding window ensures that the solution is both concise and performant, suitable for larger input sizes. Here, we begin by importing the necessary Java utilities and defining our solution class. The main method, balanced string, takes a string s as input. First, we calculate the target frequency for each character, which is the total length of the string divided by 4, since the goal is to have an equal count of q, w, e, and r. Next, we initialize a frequency map to count the occurrences of each character in the string. We then populate this map using a for each loop. After building the frequency map, we check if the string is already balanced by calling the helper method isBalanced. If it is, we immediately return 0, as no replacement is needed. If not, we proceed with a sliding window approach to find the minimal substring that can be replaced to achieve balance. We initialize variables min_length to store the shortest substring length and left to serve as the starting point of the sliding window. As we iterate over the string with the right pointer, we decrement the count of the current character in the frequency map, simulating its removal from the window. Now, we adjust the left pointer of the sliding window. While the substring defined by the current window satisfies the balance condition, we calculate the length of the window and update min_length if the current window is smaller. To maintain the sliding window, we increment the count of the character at the left pointer back into the frequency map and move the left pointer forward. This ensures that we continue exploring smaller possible substrings. After iterating through the entire string, the method returns min_length, which represents the length of the smallest substring that can be replaced to balance the string. The helper method isBalanced checks whether all character counts in the frequency map are less than or equal to the target. This ensures that the substring outside the sliding window can achieve balance when replaced. By combining the sliding window approach with the frequency map, this implementation efficiently identifies the minimal replacement substring. Here, we start with example 1, where the input string is QWER. First, we calculate some initial values. The length of the string, n, is 4, and the target frequency for balance is calculated as n/4, which gives us 1. Next, we compute the frequency of each character in the string using a counter, and we find that each of the characters q, w, e, and r occurs exactly once. Since all character frequencies are less than or equal to the target of 1, the string is already balanced. Therefore, no replacements are needed, and the result is 0. This simple case establishes the baseline for how we determine balance in the string. Now, let's move to example 2, where the input string is QQWE. We start with the same initial setup, the length of the string is 4, and the target frequency remains 1. This time, when we calculate the frequency of each character, we find that Q occurs twice, while W and E occur once each. Since Q exceeds the target frequency, the string is unbalanced. To fix this, we apply the sliding window approach. We initialize min_length to the length of the string, which is 4, and set left to 0. Then, we begin expanding the window by iterating over the string. At right equals 0, we decrease the count of Q by 1, making the count for Q, W, and E all equal to the target. This means the substring, left to right, or Q is valid. We update min_length to 1, as this is the shortest balanced substring so far. Afterward, we shift the left pointer and restore the count of Q, preparing for further iterations. Expanding the window further, we repeat the same process for the remaining characters in the string. At each step, we adjust the frequency counts and check if all characters are within the target. Ultimately, the shortest valid substring we find is Q, and its length is 1. Thus, the output for this example is 1. Moving to example 3, we now consider the input string QQQW. Again, we start with the initial setup, the length of the string is 4, and the target frequency is 1. The frequency count reveals that Q occurs 3 times, while W occurs once. Since Q greatly exceeds the target, the string is unbalanced, and we proceed with the sliding window approach. Using the sliding window approach, we initialize min_length to 4 and start with left at 0. At right equals 0, we decrease the count of Q by 1, reducing it to 2, but the string remains unbalanced because Q still exceeds the target. At right equals 1, we decrease the count of Q again, bringing it down to 1, which achieves balance. The substring, left to right, or QQ, is now valid. We update min_length to 2, as this is the shortest valid substring found so far. We then increment the left pointer, restoring the count of Q to 2. Finally, as we continue expanding the window, we find that the shortest valid substring remains QQ, with a length of 2. Therefore, the output for this example is 2. This demonstrates how the sliding window technique efficiently identifies the shortest substring needed to balance the string. In this solution, we use the sliding window technique along with a hash map to efficiently manage character counts. Let's start by analyzing the time complexity. First, the initialization step involves creating a frequency count of all characters in the string using the counter function. This operation scans the entire string once, making it an O(n) operation, where n is the length of the string. Next, we handle the sliding window traversal. The outer for loop iterates through each character of the string exactly once, resulting in O(n) iterations. Within the loop, the left pointer adjusts dynamically to maintain the balance condition. While it may seem like the left pointer introduces additional iterations, its total movement across all iterations of the for loop is amortized to O(n), because each character is processed no more than once. Together, these steps ensure that the sliding window traversal contributes O(n) to the overall time complexity. Now, within the sliding window traversal, we also check if the current window satisfies the balance condition. This involves evaluating whether each of the 4 specified characters Q, W, E, and R meets the target count. Since there are exactly 4 characters to check, this operation is constant time, or O(1). When we combine all these steps, the total time complexity of the algorithm is O(n). Let's move on to the space complexity. The memory usage is primarily determined by the counter object, which stores the frequency counts of at most 4 unique characters. Since the number of keys in this hash map is fixed, it uses O(1) space. Additionally, variables like n, target, min_length, and the 2 pointers left and right also take constant space, contributing O(1). Finally, the input string itself requires O(n) space since it's part of the function's input. These components together result in an overall space complexity of O(n), dominated by the input string. With the auxiliary space being O(1), aside from the input string, the total space complexity remains O(n). Let's compare this optimized sliding window approach to the brute force method. A naive solution would involve generating all possible substrings of the input string and checking if replacing any substring results in a balanced string. Generating all substrings requires O(n) squared operations, and checking the balance condition for each substring adds another O(n), leading to an overall time complexity of O(n) cubed. In contrast, the sliding window approach eliminates the need to enumerate all substrings by dynamically adjusting the window bounds, reducing the time complexity to O(n). The space complexity for both approaches is O(n) due to the input string, but the sliding window technique is clearly far more efficient in terms of execution time, making it the optimal approach. To understand the algorithm's behavior in different scenarios, let's look at the best and worst cases. In the best case scenario, if the string is already balanced, the algorithm completes after the initial check using the all function, which takes O(n) time. No further sliding window traversal is required. In the worst case scenario, the algorithm processes the entire string, with both the right and left pointers iterating through the string. Even in this case, the total operations are bounded by O(n), due to the amortized analysis of the sliding window. Overall, the time complexity remains O(n) in both scenarios. Mathematically, this is because each character is processed at most twice, once when expanding the window and once when contracting it. Since all operations within the loops are O(1), the runtime is guaranteed to be O(n). Similarly, the space complexity is dominated by the input string, resulting in a final complexity of O(n). When solving this problem, there are a few common mistakes that many candidates encounter. First, overlooking edge cases like empty strings, strings with all identical characters, or strings that are already balanced is a frequent pitfall. Neglecting these scenarios can lead to runtime errors or inaccurate results, so it's important to test your solution against them to ensure robustness. Next, inefficient computation in a sliding window approach is another common issue. If the window adjustment logic is misplaced, you might end up rechecking the same substrings repeatedly, which unnecessarily increases time complexity and could result in a TLE time limit exceeded for larger inputs. Another mistake to avoid is not optimizing the updates to character counts. Instead of recomputing the frequency for the entire window every time it slides, aim to update the counts incrementally. This reduces overhead and keeps the solution efficient. Finally, some candidates resort to brute force methods for long inputs, generating all possible substrings. While straightforward, this approach leads to exponential complexity and is impractical for large datasets, as it won't meet time constraints. Hardcoding specific string patterns is another mistake to watch out for. For instance, assuming only lowercase English letters in your solution can make it non-scalable and unable to handle diverse or custom character sets. Instead, your solution should be generic enough to adapt to various inputs. From an interview perspective, there are several key insights to keep in mind. First, focus on recognizing patterns. Many problems, including this one, can be tackled with techniques like sliding windows, prefix sums, or greedy approaches. Being able to identify the right pattern quickly is a crucial skill. Additionally, always consider the trade-offs between space and time complexity. For example, some problems allow for O(1) space solutions using pointers or in-place techniques, but it's a good idea to clarify constraints with your interviewer before committing to an approach. Testing your solution early and often is another best practice. Dry run your logic with multiple examples to catch potential issues before you finalize your code. And if time is running out, make sure to explain the trade-offs in your approach and highlight potential optimizations. This shows critical thinking and problem-solving ability, which interviewers value highly. This problem also shares similarities with several other LeetCode problems that you might find useful to review. For instance, LeetCode 424, longest repeating character replacement, involves a sliding window technique where you replace characters to achieve a desired outcome. Similarly, LeetCode 567, permutation in string, uses sliding windows and frequency counts to check for permutations. Another related problem is LeetCode 1004, max consecutive ones 3, which focuses on adjusting a window to satisfy constraints. And then there's LeetCode 76, minimum window substring, a classic example of sliding window optimization challenges. Apart from related problems, there are alternative approaches you could explore. For example, a brute force method involves generating all possible substrings, modifying each one, and checking if it meets the constraints. While simple to implement, it's highly inefficient with a time complexity of O(n) cubed, or worse. On the other hand, an optimized sliding window approach allows you to dynamically adjust the window while maintaining the balance condition. This is far more efficient, typically O(n), but it does require careful implementation to avoid boundary or off-by-one errors. Another option is using prefix sums, which pre-computes results for quick lookups. This is particularly useful for range-based problems, though it may require additional memory, making it less suitable for environments with tight space constraints. Finally, the greedy approach is another alternative worth considering. This method involves making local optimal choices at each step to simplify the problem. While it can be effective for certain scenarios, it doesn't always guarantee a correct global solution, especially in more complex problems. Understanding when and where to apply this technique, and recognizing its limitations, is key to using it successfully in your problem-solving arsenal. Great work making it to the end. We summarized the key points, highlighted the takeaways, and emphasized the importance of optimization. If you enjoyed this breakdown, be sure to like, subscribe, and stay tuned for more engaging coding solutions. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!